Good evening, Carmarthenshire. This is the ABC of galaxy evolution. And what I'm talking about this evening is how the universe came to look the way it does. So we know if we look out there, we see lots of these things, these structures that we call galaxies, huge star cities containing perhaps billions, perhaps even trillions of stars. And we see all sorts of structures. Some spiral with this odd bar down the middle, and some, less interesting, simply the shape of rugby balls. But how did we get a universe full of galaxies, and how did we get such a diverse collection of sizes and shapes of galaxies? Looks like we have somebody else to admit. Okay. Let me just get rid of the message that's come up. Okay. So the question is, how did we get a universe full of galaxies like these? So that's what the ABC is all about, looking at the three principal factors that determine how galaxies ended up the way they look. The A stands for accretion. Galaxies formed because matter accreted, or if you wish, accumulated under the influence of gravity very early on in the universe's history. At the centre of most, if not all, galaxies, there appear to be large black holes, so-called supermassive black holes. In some cases, matter is falling into those black holes and they are very active. In some cases, very little matter is falling into those black holes, in which case we think of them as being rather quiet or quiescent. And the C of the ABC stands for collisions, because galaxies evolve by colliding and merging with other galaxies. It's a very slow process. It takes perhaps billions of years, but that is how galaxies change over time. So we're going to be looking at the A, B, and the C. But before we jump in, let's just remind ourselves where the story starts. If we start the story at the beginning of everything, the universe, as far as we can tell by observation, the universe seems to have come into existence 13.8 billion years ago. And when we look at galaxies, we find that they are moving away from each other. The universe appears to be expanding. And that tells us that in the very early universe, everything must have been a lot closer together. So at the moment, the observable universe, everything that we can see, is inside a sphere with us at the centre, and the sphere is some 100 billion light years across. But if we wind the clock back to the very early universe, instead of all of these objects being billions of light years apart, everything in the observable universe must have been much closer together. In other words, separated by not billions of light years, but centimetres. It's difficult to imagine everything that we imagine in the universe being concentrated into such a small sphere. I like to think of it as a golf ball because A, it's about that size, and B, a golf ball has got dimples. And we think that the very early universe had a variation in density and temperature, which we can think of, as it were, as being dimples in the golf ball. The universe expanded, and after a little while it released the light of the early universe, which we see today as microwaves. So the entire universe is bathed in microwave radiation. And it's not perfectly smooth, it's mottled. Just like the dimples in the golf ball, we see the pattern of those dimples in the sky when we look at the microwave radiation. But how did we get from that very early universe, when everything was very close together, to what we see today? The picture on the right is a picture from the Hubble Space Telescope, which shows us a tiny patch of sky that's absolutely full of galaxies. From that we deduce that the observable universe appears to be full of perhaps 1 trillion or so galaxies. To try and understand how we go from a very hot, very compact object billions of years ago into the structures that we see today, we have to rely on simulations. We can observe galaxies, but that only gets us so far. If we put the physics into a computer code and run simulations, we can get an idea of how the universe has changed over the billions of years since it was born. And there are lots of simulations because computer power has increased so dramatically over the last 10 or 20 years. It's now possible for people to run lots of different types of simulation. And I'm not going to cover them all. I've just chosen one particular family of simulations, and I'm going to use some results, some pictures and videos from those sets of simulations to illustrate this talk. The first simulation gives us an idea of how we go from a very compact universe, which is tiny and has a few dimples in it, to the structures that we see today. All we need effectively is to let gravity do its stuff, and then we'll see what structures we end up with. So the simulation takes a small part of the universe full of matter with small variations in the density and the temperature. So here it just looks a sort of uniform blue, but there are small variations in density. And if we let gravity do its stuff, those small, more dense regions will collapse and the density variations will be exaggerated. So let's run this simulation over a few billion years and see what happens to our early universe as structures start to collapse. Notice that some parts are ending up rather bright white. Those are the more dense regions, and other regions are getting a little bit darker. So structures are starting to evolve. This is a very large scale, so this is not looking at the scale of stars or galaxies. This is looking at the scale of many thousands or millions of galaxies. And you can see that the galaxies aren't randomly distributed. The white dots here appear to be along particular structures. They're grouped together, in some cases in large clusters, and they seem to be joined by these filaments that take us from one group of galaxies to another. So we end up with a sort of web structure with these filaments and some regions where there appear to be very few structures at all, very few galaxies forming. So we're going to look in more detail at these white blobs to see what's actually happening in just a moment. But this is the sort of picture that we get. We end up with a universe which is made of a web in which galaxies appear to be where these filaments of the web structure meet. We get these dense knots, and this is where individual galaxies and galaxy clusters start to form. It's thought that the hydrogen in the early universe flows through these filaments and starts to collect at these knots, which form ultimately the galaxies. If we want to simulate the universe, well, we can do that in a computer code, but how do we know that we're getting something useful out of the simulation? We can ask ourselves, if the simulation runs, do we end up with a universe full of galaxies that look similar to the sort of galaxies that we actually see when we look through telescopes or use sophisticated cameras? This is a picture of 100 or 200 galaxies that have been taken at random, a sampling of the galaxies that we see in the universe, and they've been put onto this grid to highlight the fact that they are often quite different. Some galaxies are slightly blue in colour, those on the left. Some galaxies are slightly reddish in colour, those on the right. And the structures are often different as well. The ones on the right look like relatively amorphous rugby balls, so-called elliptical galaxies, and the ones on the left have a more spiral structure. Sometimes the spiral arms of the galaxies are very obvious, sometimes less so. So if a simulation is going to be useful to us, it ought to be able to explain the structures of all of these galaxies. So let's have a look at the A of the ABC of galaxy evolution. A for accretion. Let's see how that accretion actually works. Let's say a few words first about the simulations we're going to be looking at. This so-called Illustris project is a group of simulations looking at galaxy formation that runs from just after the Big Bang up to the present day. It's going to take into account a lot of different factors, including the fact that the universe is not simply made of gases like hydrogen and helium, but the universe appears to be made of a rather mysterious substance called dark matter. We've got an idea of how much dark matter there is, though we're not too sure what it's actually made of, but we can factor that into the simulations. When galaxies start to form, stars start to switch on, and we have to take into account the fact that stars can be born out of clouds of hydrogen. They might live, but ultimately they might die, and massive stars might die in a supernova explosion, and it might be that they form black holes at the center of those explosions. All of this has to be taken into account in the simulation, because although gravity is trying to collapse the structure into stars and galaxies, these various processes, such as supernova, might impede the infall of matter accreting to form a star or a galaxy. So all of this has to be taken into account. The simulations I'm describing, the first version of this simulation, ran for 20 million CPU hours. A CPU is just a central processing unit. Think of it just as a computer. So something like 20 million hours on a computer over the years 2013 to 2015 were used to run the simulations. And the result of those simulations was that the scientists who put the code together got a better idea of how the simulations were running and decided to refine their simulations and produce a second version of said set of simulations. Did they call it Illustris version 2? No, they didn't. Sounds like they were probably Star Trek fans, so they called it Illustris The Next Generation. So TNG is simply shorthand for the second version of the Illustris simulations. These ran for some 200 million CPU hours over the years 2017 to 2019. And in the last few years, they've been analysing the results of those simulations. The simulations ran on a supercomputer system, such as the one shown in the image there. Just to give some context, if you wanted to run this code on your own PC, on a desktop computer, you would have to run the program for some 20,000 years in order to give comparable results to the sort of results that are obtained on these supercomputers over a period of some months. Spatial scales over which the simulations ran were different. In other words, they ran over large scales to get an idea of the large scale web structure that we can see on the right hand side, but they also ran over smaller spatial scales to get more detail of what's going on with individual galaxies or collections of galaxies. And they also ran over an intermediate scale to make sure that everything looked fine. Now, you're possibly not familiar with the distances of parsecs, and these distances, the so-called TNG 50, 100 and 300 simulations, were carried out on scales of 50, 100 and 300 million parsecs. That's equivalent to about 150 or 300 or 1000 million light years. Let's just take a quick aside and remind ourselves of the difference between a light year and a parsec. A parsec is 3 and a bit light years, and amateur astronomers tend to use light years. It's a reasonable unit that most people can get their head around. It's how far does light travel in a year. So the distance between stars, our nearest star is the Sun, the second nearest star would be about 4 light years away. So 1 parsec, being 3 and a bit light years, is roughly speaking the average distance between stars. But astrophysicists are different. They prefer to use parsecs rather than light years, so we have to get used to that particular unit. If we think about the size of the Milky Way galaxy in which we live, the diameter of the Milky Way is about 150,000 light years, or about 50,000 parsecs, 50 kiloparsecs. And in terms of the distance between galaxies, to take as a rough yardstick, the distance between our galaxy, the Milky Way, and our neighbouring galaxy, the Andromeda galaxy, that distance is about 2.5 million light years, or about a megaparsec. So there's a useful rule of thumb. Parsec is roughly speaking the distance between stars, typically, and megaparsec is roughly speaking the distance between galaxies. So a useful rule of thumb there. So let's actually have a look at one of these illustrations. If you remember earlier, I mentioned the fact that this web structure was made from filaments, and where filaments meet, matter is flowing down those filaments in order to generate galaxies. And here's a close-up of one of those galaxies being formed. So matter is streaming down the filaments from the top and from the left and from the bottom. Matter is streaming in from all directions and collecting or accreting in the center here, producing this galaxy, which is swirling like water going down a plug hole. You can see that not all matter simply falls into the galaxy. It often swirls around. Sometimes it gets thrown out. You can see it's starting to get a little bit darker towards the edges, indicating the density is going down, and it's getting brighter towards the middle, indicating the density is getting higher. And after a while, you can start to see the shapes of spiral structures starting to form. Let's just run that simulation one more time. From a relatively small variation in density between the center and the edge, that density is increasing towards the center as matter is being depleted from the outer regions and starting to concentrate in the inner regions. You can see it's a very chaotic affair. There's nothing orderly about the way matter accretes to make galaxies. But you can see the swirling nature. In this particular case, the galaxy appears to be rotating anti-clockwise as seen from our particular perspective. On average, they don't rotate in any particular direction. It just depends on how the matter is falling into any particular part of this huge web of filaments that we're looking at. If we think of the simulation here shown in negative in the background here, so the galaxies are dark dots on a relatively mid-grey background. If we look at the simulation on the larger scale and zoom into particular structures, we see individual galaxies and collection of galaxies. But the question we can ask is, do these simulated galaxies look the same or anything like the real galaxies which we actually see in the sky? And if we take those simulations, those 4 little blow-ups from particular regions of this simulation, we can compare them with observations. So on the left-hand side, here's a couple of colliding galaxies, and we can say they look rather similar to this pair of colliding galaxies in the simulation. And similarly, there's a couple of interacting galaxies here, which don't look so different from the simulation here in the middle. And again, here's one particular galaxy that appears to have almost a ring or shell type structure. And again, that seems to be modeled in the simulation with some of the galaxies looking rather similar to that. So taking a 300 megaparsec scale is a fairly large scale. It gives us a good idea of the web or filament structure of the universe that's being generated. But if we want to see the detail of galaxies rather than just the galaxies on the larger scales, we need to look at TNG 50, the 50 megaparsec simulation, to get a better idea of the detail of galaxies that are forming. So here we see a collection of 25 galaxies taken from the TNG 50 megaparsec scale simulation. On the left-hand side, the coloured images are showing us where the hydrogen is collecting together, where there is high-density regions of hydrogen, yellow being high density and purple being somewhat lower density. The images on the right are the same galaxies, but this time, assuming that the hydrogen is going to make stars, this is showing us where we would expect to see the light of galaxies, assuming the hydrogen makes stars and then the stars produce visible light, which we can then see. So the right is, roughly speaking, what we would expect to see if we were to look out into the universe. And indeed, a lot of the galaxies that are produced in this sort of simulation do bear a striking resemblance to the sort of galaxies that we see if we do galaxy surveys using any telescopes, whether it be the space telescopes that we have above the Earth or whether it's the ground-based telescopes that are surveying galaxies throughout the universe. So it appears to be doing a good job of giving us an idea of the diversity of galaxies that exist. But perhaps even more importantly, the simulations generate galaxies that have a mass of some 1 or 2 or 300 billion stars that look very similar to our own Milky Way. If a simulation wasn't able to produce the sorts of galaxies in which we live, then it's not really telling us about our universe, and in particular our galaxy. So in this particular case, this simulation, we see as seen face on, we get the spiral structure, which is pretty much what we think our own Milky Way looks like if seen face on. And as seen from the side, we can see that the galaxy is relatively thin except for a central bulge there. And sometimes it's said that the Milky Way galaxy, as seen from the edge, looks a little bit like two fried eggs back to back. Relatively thin towards the outer edges, but with this bulge in the middle. So the simulation seems to be doing a good job of generating the sorts of structures of galaxies that we see, and in particular our own Milky Way galaxy. Let's have a think about the B of the ABC, the fact that galaxies contain black holes, in particular a very massive black hole at the centre of a galaxy. So how do we know what lies at the centre of galaxies? Well, it might sound very odd, but it is possible. Even if we can't see exactly what's going on with the black hole itself, we can get an idea of what's going on in the vicinity of a black hole by looking at the stars that are close to that central black hole. We can tell there's something there, not by seeing it directly, but by seeing the effect it has on other stars. So in other words, we can actually note that stars move in a particular way when we look close to either the centre of our own galaxy or the centre of other galaxies. And we get the impression that the stars are in orbit around something, but that something is often something that we can't directly see. If stars are in orbit around it, it must be quite massive. But if we can't see it, invisible but massive, that seems to be the best candidate for a black hole. In the case of our own galaxy, stars have been studied for the best part of a decade or so. So these coloured ellipses here represent the paths of stars that have been watched for more than 10 years to see how they move. They all appear to be in orbit around a central object, which is quite tiny, because notice that, for instance, the orbit of star 14 is very elongated, and the object itself cannot be very big, otherwise this star would not be able to orbit unimpeded. So if all of these stars are moving around an object, by noting how fast these stars are moving, we can get an idea of the mass that's holding them in their orbits. And it turns out that it must be a mass significantly more than the mass of our Sun. It's some 4 million solar masses. And that symbol on the right there, capital M, circle dot, is just shorthand for the mass of our Sun. There's nothing special about the mass of our Sun, it's just a convenient unit to use rather than use kilograms or tons. So this object is very massive, millions of times more massive than our Sun, but it must be very small, otherwise these stars would collide with it. And so it can be no more than, for instance, the size of our solar system, much smaller than the orbit of Pluto. And the only object that fits the bill for something so massive to be so small is a black hole. And we call them supermassive black holes because they are not hundreds or thousands of times more massive than our Sun, but generally millions of times more massive or even greater. So, for instance, within our galaxy, that's not actually a picture of our galaxy from outside. Of course, we can't do that. It's a picture of our galaxy from inside, but schematically speaking, we can say that somewhere buried in there is a supermassive black hole, which I've abbreviated with SMBH, a supermassive black hole with a mass of 4 million solar masses. We can't see it directly. It's a very dusty environment, as you can see in the Milky Way. It's not an even glow from all the stars in our galaxy. There's lots of dust, and so it's very difficult to see exactly what's going on. And that's one of the difficulties we've had in trying to see what's going on at the heart of any galaxy. But it has been possible with some different candidates, for instance, the galaxy called Centaurus A. We think at the centre there is a supermassive black hole with not 4 million solar masses, but some 100 million solar masses, substantially bigger than the supermassive black hole at the centre of our own galaxy. Now, black holes, material can fall into black holes, so we can think of that as black holes feeding. If a star gets disrupted by approaching too close to a black hole, all of the material of the star might try and get guzzled up and fall into the black hole. But just like water being emptied from a bath, it can't all go down the plug hole at the same time. So a lot of that matter, if we just run that simulation again, a lot of the matter from the black hole disrupting this star and effectively pulling it to pieces, the matter is being pulled towards the black hole, but most of that matter ends up circling around the black hole, as it were waiting its turn to go down the plug hole, a so-called accretion disk. Also, you noticed that there are jets coming out of the black hole, not from within the black hole itself, but from the region immediately outside the black hole. And the mechanism that's producing these jets is not fully understood. But any material falling into the black hole allows the black hole to generate energy and produce enormous energy into these jets. So not only is the accretion disk itself very hot and radiating energy, the matter falling into the black hole allows it to generate these very energetic jets pointing in the two different directions. Here we see a distant galaxy called M87, and there's a jet coming out of this galaxy. Well, actually, there's two jets coming out of the galaxy. One jet is coming towards us and is visible, and the other jet is moving away from us and is not so visible. If we look at the Hubble Space Telescope image, we see one jet quite distinctly coming off to the bottom right from the centre of the galaxy up here. We see this jet quite clearly. We think there is another jet on the other side, but it is not anywhere near as visible. And to see what's going on at the centre of the galaxy M87, a lot of radio telescopes were linked together into the so-called Event Horizon telescope to give us the best view yet of what's going on in the vicinity of this particular black hole. And the image it produced was this. We're effectively looking at the accretion disk orbiting around the black hole of M87. The black hole itself is given the nomenclature M87 star. And we think that the supermassive black hole at the centre has a mass of not millions, but 6.5 billion solar masses. We can't see the black hole itself. This shadow in the middle is caused by the fact that the gravity is so strong, then light from around the accretion disk is getting distorted by that supermassive black hole, and no light can reach us from that particular region. We can get an idea of what it is we're looking at from this particular simulation, which says if we have a flat accretion disk, it looks flat as seen from above, but as seen from the side, it looks rather distorted. If it is flat, we might expect it to look a little bit like Saturn's rings, but it's clearly much more distorted than that. It's not the accretion disk that is distorted, it's the fact that the light that is trying to reach us is distorted by the presence of the black hole at the centre, and so we can see the most distant part of the accretion disk. We can see the top of the disk, as it were, peaking above the black hole. Not only that, but we can see the bottom of the accretion disk coming from the other side. Things get very weird when light is distorted by the presence of a black hole. But we think that's what we're looking at when we look at this particular accretion disk image produced by the Event Horizon telescope. As well as looking at a distant galaxy, it also looked at our galaxy. So this is an accretion disk around our own supermassive black hole. That black hole is called Sagittarius A star, and as I mentioned earlier, it has a mass of some 4 million solar masses. These two pictures look about the same size, but bear in mind that the M87 galaxy is 1,000 times further away, but its black hole is about 1,000 times bigger. So in terms of the angular size on our sky, they appear to be a similar size. But in terms of their actual sizes, they are very, very different. If we think about the accretion disk of M87, then we would have to zoom into a tiny little region here at the very centre in order to see the accretion disk of our own supermassive black hole. But the energy that a supermassive black hole can generate if matter is falling into it can be absolutely astounding. So here we see Hercules A. This is Hercules A, this rather nondescript galaxy quite some distance away from us, and this is a visible picture taken by the Hubble Space Telescope. These bright objects on the side are simply stars that are in our own galaxy and just happen to be in the same line of sight. So these are nothing to do with the galaxy itself. But to get an idea of how big Hercules A is, this galaxy here, if it was at the same distance as Hercules A, this galaxy probably would be something like the same size as our Milky Way. So that gives us a sort of scale. If we were there, that's roughly how big the Milky Way would be. So you can see that Hercules A as a galaxy is substantially larger than the Milky Way. But at the centre of Hercules A is a supermassive black hole into which large amounts of matter is falling, and that is generating an absolutely huge amount of energy. That energy is enough to drive jets out of that supermassive black hole region, out not only into the galaxy itself, but way beyond the galaxy. If we look with radio waves, we see just how big those jets are. They are absolutely huge. You can see that the jets formed right at the centre of the galaxy easily are larger than the size of the galaxy itself, and some 10 to 20 times the size of our own Milky Way galaxy. The amount of energy required to make jets that go this sort of distance into intergalactic space is absolutely vast. And a supermassive black hole is the only engine that we know about capable of generating these levels of energy. Now, if a supermassive black hole is feeding voraciously, in other words, if a lot of gas and stars are falling into the black hole, then we call it an active galactic nucleus, or AGN for short. And the most energetic AGNs are called quasars, and they emit so much radiation that they can be observed from distances of billions of light years. Remember, our immediate neighbours in terms of galaxies might only be millions of light years distance. So we're talking about thousands of times further away. And despite the huge distances of these objects, they are still visible not only to very large telescopes, they're actually visible from your back garden, not with your naked eye, but as a lockdown project in the middle of 2020, when we had little else to do, I decided to try and take a picture of one of these quasars using my camera on a little star tracker that simply rotated the camera to follow the stars in the sky. And one summer's night, I pointed it at a patch of sky and caught this particular rather unassuming object indicated by the two red ticks here. I can blow it up even further. It's very unimpressive. It's just a few pixels in the image. But the light from this quasar came from a distance of 25 billion light years. This object is on the other side of the observable universe. But despite that vast distance, there's so much energy coming out of that supermassive black hole that it's possible to catch it with a camera sitting on a little star tracker. So no telescope involved, just a camera and a telephoto lens. The fact that it's possible to catch one of these objects, the light from these objects, at such vast distances, the light had to be travelling for most of the age of the universe in order to reach us. But there's still some mysteries about these supermassive black holes. We understand the mechanism that the energy is produced by infalling matter. We don't understand the details of the mechanics of how that produces jets. But we also don't really understand the relationship between the mass of the supermassive black hole and the galaxy in which it resides. So if we plot for a number of different galaxies the black hole mass on the vertical axis, And the mass of the host galaxy on the horizontal axis, strictly speaking, it's the mass of the central bulge of the galaxy, but we can see there's a relationship between the two. The Milky Way is not a particularly large galaxy, and it doesn't have a particularly large supermassive black hole. But compared to M87, that's a much more massive galaxy, and it has a much more massive supermassive black hole. And you can see that there is a rough relationship between them, as indicated by the red line. But we don't understand exactly how that relationship comes about. It's a chicken and egg problem. Which formed first? Do black holes form and then galaxies grow around them? Do galaxies form and then later the black holes come along? Or do they evolve hand in hand as the galaxy evolves in the early universe? That's one thing that the James Webb Space Telescope might help us answer. By looking into the very early universe, the James Webb Space Telescope might be able to tell us something about the early evolution of these galaxies and these black holes. So let's have a look at the C of the ABC, collisions. Galaxies evolve and galaxies grow by colliding and merging with other galaxies over timescales of billions of years. If we look at a snapshot like this, it's very easy to be fooled into thinking that the galaxies don't do much. They are effectively static, except for the fact that we know they very slowly rotate. But what this picture doesn't tell us is that over a galaxy's lifetime, it can evolve through interactions with other galaxies. We know galaxies interact with each other because we can take snapshots of galaxies in the process of interacting. So these galaxies are distorting each other and producing these gravitational tails of stars that are dragged out by the interaction with the other galaxy. So we know these interactions take place, but we can only really fully understand the influence of collisions and mergers, not by taking a lot of snapshots, but we can only really appreciate it by looking again at simulations. So let's look at an illustrious simulation on a large scale, showing us not an individual galaxy, but thousands of galaxies and how they interact with each other. And we can see it's an absolute soup of interaction. There are lots of galaxies moving all over the place, apparently at random. But notice there's a big galaxy coming in from the top and a big galaxy coming in from below. They are going to meet in the middle. Let me take the cursor out of the way, and you can see those galaxies interact with each other. They swing past each other, and now they are merging with each other. So now we have an even bigger galaxy in the center of our frame and lots of smaller galaxies zooming around. Is that the sort of thing we see when we look into the universe? Do we see big galaxies surrounded by lots of smaller galaxies? Well, quite often we do. The Milky Way itself is surrounded by dozens, if not hundreds, of much smaller galaxies. So again, this simulation gives us some reason to believe that this is indeed modelling the universe in which we live. Let's just run that simulation one more time. So we see lots of galaxies moving. The more you watch this sort of simulation, the more you see. Lots of galaxies are interacting with each other. The large one at the top and bottom are going to get much closer to each other. They are going to swing past each other, and gravitationally they are then going to pull on each other and eventually merge together over a period of some billions of years. The individual stars don't necessarily collide with each other, but the interactions make the galaxies grow slowly over time. Galaxy clusters that we see using, for instance, the Hubble Space Telescope, they tend to be, like the image shown on the left here, they tend to be the redder elliptical galaxies, the galaxies that don't seem to show any particular spiral arms. So there might be a few rather bluer spiral galaxies in there, but crowded galaxy clusters often have a much larger fraction of the redder elliptical galaxies. And that's because a crowded galaxy cluster means more collisions. And generally speaking, well, when spiral galaxies collide with each other, that results in these redder elliptical galaxies in which the individual stars are not rotating around a common axis. It's much more like a rugby ball in which individual stars are moving almost at random around the central core of the galaxy. We know that the Milky Way is at some point going to collide with the Andromeda Galaxy. We can tell that by looking at the motion of our nearest neighbour. And so we are in the Milky Way galaxy in the top right, a spiral galaxy. The Andromeda Galaxy is also a spiral galaxy, but when eventually they do collide, we're going to end up in a galaxy which is probably going to be more like an elliptical galaxy. So this simulation is showing us, roughly speaking, what is going to happen in a few billion years. As the galaxies get close to each other, their gravity will tug on each other. Individual stars won't collide, but the gravity of the two galaxies will result in the destruction of the individual spiral arms, and eventually the two galaxies will pass through each other a second time and then settle down and merge together. Eventually, the supermassive black holes at the centre of the Milky Way and the Andromeda galaxies, eventually they will merge as well. So it's going to be quite a spectacular sight. At the moment, the Andromeda Galaxy is just a relatively small galaxy. It can be seen with the naked eye, but it looks, because it's a distance of a megaparsec or so, it looks quite tiny compared to the Milky Way, which of course we're seeing from the inside, so we can't easily see the spiral arms of the Milky Way. But over time, the Andromeda Galaxy is going to grow in size in our skies because it's coming towards us. In a billion years, it'll be a spectacular sight. In 3 or 4 billion years, it will almost fill the sky. And over a period of 4 to 5 billion years from now, it will pass through our own galaxy, and there will be a riot of new star formation as the individual galaxies lose their identity and all of the gas and the dust of the two galaxies mix together and make new stars. So at some 4 billion years into the future, the sky is going to be alive with new star formation. For a little while, the Andromeda Galaxy will have passed through the Milky Way and out the other side, but over the next few 100 million years, they will settle down and eventually merge together into one large elliptical galaxy. What we call that galaxy, well, I don't know what we're going to call it. We can't call it the Milky Way anymore. It's not the Milky Way, it's not Andromeda. Are we going to call it Milkdromeda or Andrilke or Androway? It's all right. We've got 5 billion years to decide on the new name for this mega galaxy. But given that these two black holes, the one at the centre of the Milky Way and the one at the centre of the Andromeda Galaxy, are ultimately going to merge together, it might well be that this new galaxy ends up as a quasar. If lots of matter ends up getting funneled into the supermassive black hole at the centre of this new galaxy, it could well be that in 5 billion years' time, our galaxy turns into a quasar and ends up generating so much energy that the jets that are produced could be visible from the other side of the observable universe in much the same way that I demonstrated at the moment that it's possible to image a quasar from your back garden. Even though it's 25 billion light years away, perhaps that is ultimately the fate of the Milky Way or the Milky Way Andromeda merger. So this, of course, is just an artist's impression of what that might ultimately look like. So I've given you an idea of the ABC of galaxy evolution, how they're born and how they evolve. They're born through accretion, with matter accreting under the influence of gravity from the very early universe after all of the hydrogen was made in the Big Bang. At the centre of most, if not all galaxies, there appears to be very massive, so-called supermassive black holes. In some cases, matter is falling into those black holes and they are very active. In some cases, very little matter is falling into those black holes and the black holes are quiescent, much like the one at the centre of our Milky Way. And all galaxies evolve through collisions and mergers, through a cannibalization process, one galaxy will eat its neighbors and grow over a period of billions of years. So next time you see a galaxy, either if you're lucky enough to look at a galaxy through a telescope with your own eyes and admire the structure, or if it's simply admiring the results of the Hubble Space Telescope or the recently launched James Webb Space Telescope, next time you see a galaxy, remember how they came to be, the ABC of galaxy evolution. Thank you for listening.